Okay. Yeah, you're up to about 90 with more coming in. Okay, a little hiccup there. I'll start over. So homework 5 was due today at noon, and hopefully you got that in. No office hours on Thursday because I had moved them up to Tuesday for all of you who wanted help with the math. And it was just one person showed up, but that person showed up like 4 times, so it was okay. But take advantage of my office hours if you want to. They're there for that. Otherwise, I'm just sitting here by myself, very sad, very lonely. No, it's I have plenty to keep myself busy if you don't attend, but I'm here. Homework 6 is due, let's see, I have it here, a week from Friday, tentatively. We'll see how far we get. If I have to move that one back, I will. Hopefully I've been catching up a little bit. But the classes are scheduled a little bit differently than I normally do, given the different start date for the semester. So even though we're running late on every homework, I think I'm actually a little bit ahead of schedule. Just the homeworks got scheduled a little bit off. But we'll see as we approach the end of the course. Also, there's an extra credit opportunity. And it's not for everyone. It's if you, well, as you probably know by now, I drop one homework automatically. And so if you had one that you bombed or you forgot to do, not a problem. But there's a second one, I'll drop a second one if you do the extra credit homework. So it's really only if you bombed 2 of them or forgot to do 2 of them, had technical difficulty, that kind of thing. If you had a medical excuse documented, we'll give you an extension, but anything else, no. But the extra credit assignment is in the ebook. So you go to the ebook, which I have already loaded up here. It's under lesson 5. And as you go through this, you may notice that when we get to the part about exploration of the solar system, there's this long list of pretty much every mission to the planet over the years. It's maybe a couple years out of date now, but you're not responsible for all that information. It's there primarily for those who are doing the extra credit assignment, which is down here at the bottom. And the idea is you pick one mission from that list, or a more modern one if the list hasn't been updated recently, or a series of missions, the same kind of mission where they flew it multiple times, and write a 2-page essay. You just have to remember to follow the rules. There's certain rules about font sizes and font types and margins and single space, and you got to go one line onto that 3rd page. And if you don't follow the rules, then it gets, it's either counted or it doesn't count. There's no grade on this. If it counts, I drop a second homework. And if you kind of cheat the system a little bit, you do like 2 3/4 or 1 3/4 pages, then it doesn't count. Or if you double space, or if you do the 1 1/4 space. I know all the tricks. I was a student too. And now that I'm a grant writer, I use the tricks in reverse, trying to compress things into space. But anyway, it's pretty straightforward. Just research one of those missions, write about it, don't plagiarize. I will grab a sentence or 2 and throw it into Google just to see. If you plagiarize, then it's an honor court possibility. But otherwise, it's pretty straightforward. Again, it's not for everyone. It's just if you need to get rid of a second homework, it's there. I just want to mention it at least once. Sometimes I forget to mention it at all. Someone's calling me. I forgot to mute my phone. 1 second. How rude of me. Okay. I think that's it for announcements. Any questions about any of that? Okay. Let's see. We have a couple things. There's a video I was going to show you last time just because it's kind of fun. You all probably have seen it at one point, but this was the SpaceX Falcon Heavy landing. You've seen plenty of launches, but again, we were talking about new space, and the innovation of SpaceX is to return the vehicle to Earth so you can reuse it. You don't have to pay all that money to build a new one. Falcon Heavy has 3 of their Falcon 9 rockets strapped together, and it left from Florida, and 2 of them landed back there, and 1 landed off crash landed on a barge. The barge landings, they've gotten better at them since then. But I'll just play kind of the final minute of the landing. I'll turn the sound off. So what we're looking at, these are two separate cameras, one on each of the, well, three separate cameras, one on each of the boosters, and they're coming back down. The top left one here is going to the barge, and there's a lot of precipitation. It's over the ocean, and it didn't make it. But here you see one of the ones coming down into the launching pads at Florida, Cape Canaveral. It's firing. It almost looks like the same video, but it's actually two separate rockets. They're two pads next to each other. And here you can see them landing. I mean, to within like half a second of each other. So if you've never seen it before, hopefully you're impressed by that. I found, this is the one where he put his Tesla into Mars orbit, and a lot of people were impressed by that. But that's really just more of a gimmick and something to draw attention to the progress they've made. But to me, that was the most impressive part of the launch. I don't know if they've launched the Falcon Heavy since. I think maybe once. I can't recall for sure. Here's the barge, and before and yeah, after. You can't see anything there, but okay. I don't want to load the next thing. I want to save this for the next class. Okay.
Dr. Reichert.
Yeah, go ahead.
This might sound like a little bit kind of going off topic, I guess, from what we're learning, but like, why did it take so long? Or like, why didn't people attempt to like try to use like reusable rockets as like a thing? Like, why did it take SpaceX for them to figure it out?
It seems obvious now, doesn't it? All right. Because I gave the analogy of building a 747 and flying it across the country and ditching it in the ocean every time you flew. It seems like the obvious thing to do. And, but yeah, the idea never came up within NASA, or if it did, it wasn't taken seriously. And this is where, the private marketplace and in kind of our system of economics can actually be beneficial. If there's a profit motive, that often spurs new ideas. It's a huge incentive to innovate and come up with new ways of doing things.
Is Homeboy back? It's showing that he's the host now. I don't know where he is.
His audio is connecting.
All right, so I'm back. Yeah. Whatever. Yeah, most of you still here, it appears. Okay, so let me share my screen. And we'll get a dot cam back up. Right, so the question was, why haven't we thought about reusable spacecraft previously? And I think just the idea came out of private industry. Government operations can get things done quickly if there's sufficient money thrown behind them. But that hasn't been the case with NASA for some time. And with proper incentives, people can be very creative. Now, let's see. We had I'm just waiting for my web page to come back. It's not responding. My computer reloads. Well, I'll just do it verbally, I guess. So we have a warm-up question here, and then we'll get into the new material with lesson 6. So this is left over from lesson 5. Last thing we talked about is calculating densities and using these densities to determine what kind of world we're talking about. Here are the 8 planets in our solar system and their average densities. The question is, which of these planets is made primarily of rock? So 1, 2, 3, 4, 5, 6, or 7. Well, just since my web page doesn't seem to be working, I'm not going to close it because I may lose my Zoom session. But just tell me which planet of these is made primarily of rock. Just shout it out.
Mars.
Mars. Yep, that's right. And here's just a reminder. Things of these densities, water is typically about 1,000 kilograms per cubic meter. Gravitationally compressed gas is also that, because just because you see density doesn't necessarily imply what it's made of. You got to take it into context as well. But rock is in the 2,000 to 3,000 range. Metals, the primary metal in planets is iron. It's about 8,000. And just checking, let me see if we're recording, because we're supposed to be recording as well. Yep, we are. Metals is 8,000. So Mars clocking in at 3,900. It's rocks with a little bit of metal thrown in to boost the density a little bit. Okay. Let's get into the new material, and I'll try to go at a good speed to make up for lost time there. So into lesson 6, this is the part of the course where I'm going to go through the planets in great detail. This is something that astronomers are always a little bit, yeah, really? Okay. The astronomers are always a little bit nervous about, because astronomers, when we're trained in our PhD programs, astronomy, astrophysics, our departments, our programs, it's from the closest stars on out. We don't really study the solar system. And the solar system is studied, it's just by a different group of people called planetary scientists. And they have their own departments, and there's a lot of geology mixed in. And the planetary scientists, a lot of them go on to build the spacecraft that we use to explore our solar system. Astronomers, we use telescopes and we peer much farther out. For the longest time, these were separate fields. And at most institutions, they don't have any planetary scientists, so they call on the astronomers to teach Astro 101, and we kind of fake our way through, never having taken it, except when we took Astro 101 as undergrads. But the fields have merged a lot over the past decade or two. We've discovered thousands of planets around other stars. And they're far enough away that we can't send spacecraft to them. And there, my web page has come back. We can't send spacecraft to them. We have to do all this work with telescopes. So it falls upon astronomers to do this. And in the process, we've learned a lot about planets. Mostly bulk properties. It's hard to get detailed information on these very far away planets around other stars. We get some information, but to really study planets in detail, we're still limited into the worlds in our solar system. Anyway, I've been a fan of the topic ever since I was a kid, so I do know a fair amount about it, and so I should be able to fake my way through for the rest of the course. I've been doing it for almost 2 decades now here, so. Okay, so lesson 6 is going to be on the Earth and the Moon. We're going to start with the worlds that we understand very well. And then once we have those under our belt, we can reference back to them as we try to understand the other worlds out there. Lesson 7 will be the Earth-like rocky terrestrial planets. And lesson 8 will be the Jovian gas giants. Now, the book tackles the worlds, all these worlds in detail, and they're not always consistent with how they present the information. So I've reorganized it a little bit. As you're looking at the reading assignments, instead of just saying read chapter so-and-so, I'll do it by subsection, and I'll move things around a little bit. At least that will match how I try to present it in lecture. To keep kind of a consistent approach, I'm going to go through all these worlds from the inside out. We'll start with the core, the interior, which is the core and the mantle, work our way up to the surface, and then the atmosphere, if it has one. The magnetosphere is an exception. That's usually the next, it hovers above the Earth, but it's generated from the core. So we'll deal with that when we talk about the cores. And then if there's anything in orbit like moons or rings, we'll tackle those. So we'll do everything in order. Okay, so let's start. We'll spend a couple days talking about the Earth, and then we'll get to the moon. And we'll start with Earth's interior. Should be able to get through that today. So here we have the Earth, 2 pictures of it from either side, stuff you've seen before. Let's move into the interior here. And I should ask the question before pulling up the slide. The slide kind of gives away the answer. The question was going to be, how do we know anything about the Earth's interior? I mean, we've drilled holes in the past, in some pretty deep holes and mine shafts and things like that. That's all within the crust. That's this really thin layer out here. In this cartoon presentation, the crust is way too thick. The crust is actually much smaller than what's been depicted here. But we've just really drilled into the crust. We've never gotten down into the mantle or the core. The question is, how do we know anything about this interior? And again, the slide gives it away. It's from earthquakes, the process of seismology. Put that down here.
What's stopping us from drilling deeper, like into the mantle and the core and stuff like that?
Probably just technology. I mean, as you drill deeply, if you go too deep, then the deeper you go, the more pressure there is. So if you create an opening, pressure is going to want to push things into that opening. And so, once you get deep enough, it would probably try to collapse on itself. You just keep pulling out material. It's like if you're digging a hole, but the bottom just keeps caving in as you're digging. Yeah. But we can learn a lot about the interior from seismology. Earthquakes go off kind of randomly, at least in time. We know where they're going to go off for the most part, and you'll see why in a bit. But in time, they're not super predictable. But when they do go off, they send these waves throughout the planet, and these waves reemerge all across the surface or across most of the surface. And we have seismographs on the surface and also on the ocean floors where we can detect these. And what comes back out, we can use that information to figure out, well, what did it have to go through to now look like this when it comes back out? We put together this mantle core picture. But let's talk a little bit about how the waves propagate. You can see here the earthquake is going, and some waves are going straight down towards the core, and some waves will be going up various angles in this direction, also angles in the other direction that we don't see in this cutaway. It's sending waves, radially in all directions through the planet. And the waves that are going straight in continue to go straight in, but those at an angle will bend as they go deeper into denser and denser material. And this is a phenomenon we've encountered before. Anyone want to guess the word? What do we call this? It's one of the fractions. Which one is it? Not math. Yeah, refraction. Yeah, not mathematical fraction, but yeah, refraction. We encountered this with refracting telescopes. If light is traveling from a less dense medium into a more dense medium, and if it impacts it at an angle, that changes the angle. We talked about these kind of cartoon methods for remembering which way it bends. And so that's what's going on here. The waves, as they're going down in the denser material, are being redirected back to the surface, where we can record them and try to figure out what happened. Now you can see in this diagram there are 2 types, P waves and S waves. Pressure waves and S, they're transverse waves. Maybe S stands for sideways. Here's the difference between them. S waves, it's kind of like when I had the spring many classes ago and I'm shaking it up and down. That's a transverse wave or a sideways wave, it makes an S shape. The P waves are pressure waves, like sound waves are pressure waves in gas. I'm shaking my vocal cord. It's compressional, compressing, decompressing, compressing, decompressing the air. And these are P for pressure waves. So we send both types of waves out, but not both types make it back. In some regions, like here on this side of the planet where the earthquake occurred, we get both P and S waves at the surface. Our seismographs can read, how is it being shook, compressionally or transversely. But on the back side of the planet, there are no S waves. There are P waves in kind of a funny distribution, and we'll get to that distribution in a second, but there are no S waves. And the reason why, and kind of the only possible explanation, is P waves will go through anything. P waves go through solids, liquids, gas. Clearly they go through gas because I'm talking and it's making it to my microphone over here and then sent to your speaker, and it's shaking the air and going to your ear. So it goes through gas and anything. If you knock on a door, the sound wave made it through. But S waves, they don't. They fall apart unless you're in a solid medium. To understand this, you have to kind of know the difference, or understand the difference between what makes a solid solid and a liquid liquid. So a solid, these big circles represent molecules. And a solid, you're kind of in this crystalline rigid structure, and all the molecules are locked together by intermolecular bonds. The molecules feel electrostatic forces from the molecules next to it, and it locks them into this kind of rigid shape. Now, if you provide enough energy, you can break those bonds and you're no longer a solid, you're a liquid. The molecules can roll around each other. That's what we see here. They're still right up against each other. If they're not up against each other, if there's space between them, they're kind of bouncing off each other. That's the gas state. So that's the difference between the three states. Anyway, with a solid, imagine me coming over to this side of the screen and grabbing this. It's kind of like chain mail, like they wore long ago when they were jousting or whatnot. You have all these links, and you could grab one side, and if I shook it up and down, that would set off a chain reaction. If this first row went up, because of those intermolecular bonds, it would pull the next row up, which then pulls the next row up. And if I go down, and then it pulls it back down and pulls the next one back down. So I can send a wave through it, just like, here it's depicted as a rope, but imagine it as a chain with links. As I move links on this side, then it works its way through. But imagine the wave going through the solid then up against the liquid. As this last row moves up, it may push some of these molecules up, but they're not connected to the next row of molecules. So they're not going to pull the next row up. They'll just kind of move around and float around each other. And so the S wave will fall apart very quickly as it transitions from solid to liquid. It's like, again, instead of a rope, if this were a chain with links, and as I'm shaking it, if all the links disconnected from one another, the links would just fly everywhere. The S wave would fall apart. So S waves don't make it through liquid. They don't make it through gas. And the fact that we don't see them on the backside of the planet means that the core, the outer core anyway, has to be liquid. We have some of these waves working down towards the core. Up here, you're going through mantle and you're curving back to the surface. But there's this critical path right here where if you're a little bit above it, you stay within the mantle. If you're a little bit below it, and all these angles below, you enter the core. And since S waves don't make it out, that means the outer core is liquid. Not liquid water. You can have many things in a liquid state. As we'll find out, this is liquid iron. And then the other thing you notice, so yeah, only the P waves make it to the backside, but you have this, we call it a shadow, an earthquake shadow, where through this region here, we don't really see anything, maybe a few weak P waves, but they don't really start up again until here on the very opposite side. And that's because the transition from mantle to core is stark. There's a big jump in density. As these are working their way down through the mantle, it's gradually increasing the density, which gradually changes the direction. But you hit the core, there's a big jump in density. It's kind of like when we went from air to glass with a refracting telescope, you'll have a sharp change in direction. So there's nothing that gets dumped out here, but the P waves will be dumped out here. Anyway, using this information, what we find on the surface, where the shadows are, what types of waves we find, how strong they are, we can work backwards and figure out what the interior must be like. It's actually not that hard to do. And this is the picture that we get. We can measure the densities. And so here's the mantle, which is primarily rocky. You can see the densities start around 3,000, which means, just as we saw in the warm-up question, primarily rocky. The deeper we go, the densities go up. But that's because the deeper you go, there's more earth above you squeezing down and increasing the pressure, increasing the density. Then you have that sharp jump, and the core is between like 10 and 12,000. And that's iron. Iron, as we saw, is typically 8,000, but if you have half the Earth above it squeezing down on it, you can squeeze it to slightly higher densities. So we get a pretty direct measure of the density distribution. We can also figure out the temperature. Now, we don't have any thermometers in there. Again, we can't drill holes and put temperature sensors down there, but it's just basic physics. If you know the density and if you know the pressure, which we can figure out because we understand how gravity works, you can calculate the temperature. So on the surface, the temperature is like room temperature, quite low. In the interior, it gets up to about 6,000 degrees, which is the same temperature as the surface of our sun. Now, you know, the center of the sun is way, way hotter, but the surface of the sun is about the same temperature as the center of the Earth. Okay, so, well, before we get to this biologically suggestive figure here, question is, how did we get this division between mantle and core? Out there in space, iron and the things that will result in rocks, all the gases are pretty uniformly mixed. Yet here in our planet, there's a division. The heavy, denser stuff is at the center and the lower density stuff is riding higher up above it. And so this is a process we call differentiation. We'll see it over and over again. And the requirement for differentiation to take place is the planet had to be molten in the past. If it's molten, then heavy stuff can sink to the bottom and lighter weight stuff will float to the top. Low density stuff will rise, higher density stuff sinks. And I have a demo to show that, so I'm going to flip this around and we'll have a demo today. Maybe I'll move my portable microphone over there. Okay, so this was a fun demo to prepare. First, I had to get a giant tub of Cheetos, and then I had to empty the tub, so I did that for you. And I have two types of balls here. I have golf balls, which are denser, and then I have these wiffle golf balls, which are lower density. And when the Earth formed, everything's just coming in from space, and so it's all evenly mixed, but somehow the heavy stuff ended up at the bottom. I'm going to make it even more challenging. I'm going to put the heavy stuff on top. So there's a bag of Jimmy John's. I had to have a bag to hold the golf balls. So, you know, again, sacrifice there. And the lid. Here it is. So what we have here is like a solid. Nothing's moving. I'm going to shake it, which makes it like a liquid. And you'll see that the denser stuff does sink to the bottom. Be a little loud, but here we go. So I think you can see it's not perfectly separated, but most of the lightweight stuff, the wiffle golf balls are on the top, and the denser real golf balls have moved to the bottom. So the fact that Earth is differentiated just tells us that Earth was molten for some time. I don't know about you all. I made use of the same phenomena as a kid. If I want to get the treat out of the cereal box, if I knew it was lower density than the cereal, then I shake it and it rises to the top. If it's higher density, I shake it, it goes to the bottom. Then I turn it upside down and open the cereal box upside down. Drove my mom crazy. But anyway, you've probably done similar things. That's differentiation. Okay, so we're molten in the past, and why were we molten in the past? Well, the process of forming a planet is very hot. As that material comes in, it picks up speed due to gravity, and then it hits at high speed, transferring its energy of motion into heat, and it warms the planet. So when you form a planet, it forms hot, and then Earth continued to be bombarded pretty heavily for the first 500 million years, as we'll see from the lunar cratering record. And some of that material was radioactive, decaying. And that also kept the Earth warm for quite some time, about 500 million years. And that's enough time for all not all, but most of the iron to settle in the core. Fortunately, it was not a perfect differentiation. If it was, and all the iron went in the core, we'd have nothing to make steel, which is a very important component for modern civilization, buildings and planes and all sorts of things. It would suck to build civilization without metal. And so it's good that we didn't have complete differentiation. Okay, so the core. Now the core is divided between two parts, the outer core, which has to be liquid because the S waves didn't make it through, and the inner core, which, well, we don't have any direct measurements, but according to physics and our understanding of physics, it's probably solid. And you may think that's strange. You know, the outer core is warm enough to be in a liquid state. It's iron, but it's hot enough to be liquid. If I go deeper down, it's going to be even hotter. And normally, the hotter you make something, it's going to be even more liquid or just as liquid. If I cool it, a liquid can become a solid. But if I make it hotter, it's not going to become a solid. Yet the inner core is probably solid, but for a different reason. You know, the temperature is indeed higher down there, but the pressure is greater. And the state of a material depends not just on the temperature, but on the pressure. We don't think about that on the Earth's surface because it's always one atmospheric pressure. But as you're going through the Earth, you have all sorts of different pressures. And so the temperature is high enough to break all those bonds. All those little links are gone. But because of the pressure, everything's compressed into this kind of rigid crystalline solid. So it's a solid by pressure instead of by intermolecular bond. Okay. And now let's talk a little bit about the magnetic field, because it's generated in the core and it's generated in the outer core in particular. So to have a magnetic field, I'm going to put this on the dot cam because this is important. We're going to see this over and over again. To have a magnetic field, it's kind of two criteria. The first is you must have a conductive fluid layer. It has to be conductive, meaning charges can flow through it. And it has to be fluid so you can churn it up. You know, liquid iron. Iron's a metal, metals are conductive, so charges can flow through. If you want to make a magnetic field, you have to have charges going in loops. If you have charges going in loops, it generates a magnetic field in the perpendicular direction. So if we have a layer that's conductive, charges can flow, it's fluid, so you can get it moving in these loops. That is a necessary condition, but it's not sufficient. You can maybe get a weak magnetic field if you have just that. But to have a strong magnetic field, you also have to have the second condition of rapid rotation. The planet has to be spinning quickly to churn up those little eddies, those little currents in the conductive fluid layer. Earth spins once a day, and the solar system is pretty convenient. Everything is either spinning once a day or faster, or once a month or slower. So Earth's in that rapidly spinning category. We do churn up that outer core, and so we can produce a strong magnetic field. Other things like Mercury, Venus, the moon, they rotate very slowly. So even if they did have a conductive fluid layer, and we can discuss whether they do in time, they're not spinning fast enough to do anything with it. So I'll show it here. I'll show off some of my amazing Microsoft Paint skills. Since Earth is spinning rapidly, we get these little eddies down in the outer core. And when you have charges going in loops, you get little magnetic fields, and they add together to give us the global magnetic field, which is really great for us. It's our force field. It protects us from high energy charges streaming in from space. Without it, they'd just hit the ground, they would hit us, cancer rates would increase. I'm not going to go so far as to say it would make it impossible for life, but it makes it much more difficult. Instead, these charges get caught in our magnetic field and funneled to the poles where very few people live. And as they come down at high speed in those polar regions, they excite the atmospheric gas, causing green and red and blue emission lines. The blue ones are too faint for the human eye to see, but you see the green ones and red ones. And how many of you have seen the aurora? This is Aurora Borealis up north, Aurora Australis down south. Some head nods. You may not have if you're all Southerners. We're just a little bit too far south to really see it. Sometimes if there's an extraordinary one, you can see a hint of color on the northern horizon. I grew up in Pennsylvania, and even then it was really hard to see. Recently, I installed a telescope, one of the Skynet telescopes. This is in Athabasca, Alberta, Canada. It's actually an auroral monitoring station. They get a lot of aurora there. And as we were setting up this telescope, you can actually see the Big Dipper here in this picture. The aurora just turned on all around us, green and the red. The picture here doesn't do it justice. You know, it's just whatever we could quickly take while we're out there working on the telescope. And it's like curtains of light all around you. And they move. They vary on a time scale of minutes. So it's quite a thing to see if you can get up to the northern or extremely southern parts of the world. The other nifty thing about this was the coyotes. It was dark, and then this lit up the sky, and then the coyotes just started howling. And we realized they were all around us and pretty close too. And you don't realize that when they're quiet. They also howl when the new moon comes up, but the same idea, it lights up and they start talking to each other.
Dr. Reichert?
Yeah.
Just out of curiosity, and I don't know whether you'll know the answer, but you mentioned that a lot of that energy that's coming at the Earth that's blocked by the magnetic field isn't blocked in the poles. With now researchers living in the poles and much more known about them, have we seen some of those adverse effects going on there with the humans as well as the nature in the area?
Yeah, it's mostly the South Pole, of course, and we have a research station right at the South Pole. But I've never read anything about cancer rates being higher. There has been a researcher there who got cancer during the winter over, and they had to do some crazy supply drops, and you can't fly in to the South Pole during winter, but they had to do that. But that's just a single case. It's small number statistics, I think, is the answer. People have short tours of duty there. So they're not exposed long, and it's just a small number of people there. That's a valid question. Yeah, I thought about it. I had a chance to go work at the South Pole. Normally what you want is the 2-week visit, right? Because then it's all fun and games and cool. But the opportunity I had was the 6-month winter over, and I declined that opportunity. It didn't seem as much fun. Here's a picture of it taken from space, from the space shuttle. And these are just the field lines coming into the pole, and as you hit the atmosphere, you excite it, and it de-excites, giving emission lines. And the other thing about this, now I'll probably save the mantle for next time, but I know I'm going a couple minutes over, but understandable today. This is not a very steady, stable thing. These eddies, they're always changing, they're merging, they're breaking apart. And over a long time, about 1 million years, they can all cancel themselves out and restart, pointed in the opposite direction. If they point in the opposite direction, that means the north becomes south and south becomes north. Compasses flip, and they stay that way for about 1 million years. It's not predictable, it's not clockwork, but we'll see next time some studies of under the, where new rock is being laid down on either side of the mid-Atlantic trench. You can see which way the little iron oriented itself in the rock as it solidified, and keeps flipping every 1 million years or so. And this happens in the sun too. Just every 11 years, you have a field flippage there. And it's called this whole process is called a dynamo, and they're complicated, not very well understood. What is interesting is when they go through the flip, you'll have about a century of just total confusion with many poles. So there could be a North Pole coming out of Chapel Hill and a South Pole coming out of Paris, and multiple poles and little mini magnetic fields all across the Earth. So it wouldn't be like we're exposed, and cancer rates probably will go up a little bit, but we'll still be protected, just not by a big giant mega Earth-sized field. And you can see this, not the flipping, but just the constant activity down in that layer. This is where the magnetic field has been throughout time. It wanders around depending on how all those little eddies are lined up and connecting. In fact, in recent years, it's been moving pretty quickly. It's been centuries down here. Now it's just zipping past the North Pole, moving over to the Russian side. Okay, sorry about the dropout. Yeah, we've been free of those for a long time, but we got one today. And we'll pick up next time with the mantle. Now stick around for questions.
Thank you, Dr. Riker.
Doctor.
Sure.
Thank you.
Thank you.
Thank you.
Thank you.
My pleasure. Hey, Barry.
Hello.
Hey, I thought you were coming on Monday, so you saw a technical snafu today, huh?
Yeah, so Monday I got really sidetracked by an interesting classical mechanics problem and
Okay.
totally forgot because I was like heavily invested in it for our homework. And then I woke up and I was like, oh shoot, it's 1:50. It would be rude of me to join now, and I needed to observe for a whole
Sure.
lecture. So
Well, you're welcome to stick around or come back at the beginning of the next class. The beginning didn't go as normal. You didn't get to see the e-polling interface that I use. I had the question there, but the interface was still rebooting on my computer. You don't have to, of course, but the next one will hopefully be technology failure-free. And it'd be pretty much the same stuff, just slower pace, a little bit more time for interaction, and the e-polling
Okay.
interface. I had to rush it because of the technology problem today.
it honestly, to me, didn't seem like you were rushing that much.
Yeah,
I thought it was a
well,
nice pace.
yeah, I didn't open it up as much for discussion as I normally would because of it, but yeah.
Okay.
Anyway, hope you got what you needed.
Yeah. Thank you so much.
Sure, my pleasure.
See you Friday.
Okay.
Hello, Dr. Reichart.
Yes.
I just thought of something amusing that's kind of off topic, but I thought you might find this amusing. So there's this documentary about flat earthers that I saw a while ago, and I forgot what it was called, but they come up with a lot of like creative tests, like to try to prove that the Earth isn't flat. Like for instance, like using a gyroscope and waiting a really precise gyroscope and waiting some time to see if it like deviates because of the Earth's rotation, or like measuring like distances to try to calculate the curve. And like every single time they like come up with a really good test, and they're like, okay, we know what result we're going to get if the Earth is round, and we know we're not going to get this result, and they end up getting that result every single time. And it's just so funny because they try to like come up with excuses like immediately afterwards to try to like disprove their own test.
Oh, so it's done by flat earthers, and they're using the scientific method where, you know, two hypotheses make different predictions and they carry out the tests. So they're doing good science. They're just coming at it from a flat earth point of view.
Yeah,
And
it's like they spend like so much time like explaining, oh, like this test, like the way we've done it, it's like perfect. If we get this result, we know that the Earth will be round, but they get that exact result, and then immediately they're like, oh, there was something wrong with the test. Like we must have done it completely wrong.
Well, yeah, if you can find a link or something, send me that, because that seems rather amusing. Because normally with flat eartherism and stuff like that, the primary course is just denial. You live in denial and they don't think about using the scientific method. But here it sounds like they're actually trying to use the proper scientific method and they're getting results they just don't like. And so that's kind of cool.
Yeah. How should I send it to you if I find a clip?
If you just email it, I think my email address is in the syllabus.
Okay. Yeah. Thank you.
Sure.
Have a good
You
day,
too.
Professor.